Okay, let me just talk you through some graphs. We've got 3 graphs on the top and 3 graphs on the bottom. The 2 left-hand graphs, up and down, are order with reaction to A is 0, so initial rate would be K, A to the power 0. The middle 2 graphs up and down are order of reaction with respect to A is 1. And the 2 right-hand graphs up and down, order with respect to A is 2. Let's just talk them through. The top 3 graphs have got initial concentration of a reactant A and the time along the bottom, the time for the reaction to finish. Well, actually, if you look there, by changing the concentration of A, if a tangent to the graph, a tangent to those top 3 graphs gives you the rate, then the rate isn't changing, the tangent isn't changing, the gradient of the tangent isn't changing, it's a straight line. So that's why its order with respect to A is 0, because changing the concentration of A isn't having any effect on the gradient of that line. It's a straight line. Whereas if you get curves, the top middle curve, as you can see, then approximately doubling the concentration of A halves the time for the reaction to finish. So it goes twice as fast. So that could be the order with respect to A would be 1. So rate equals K, concentration of A to the power 1, doubling the concentration of A doubles the rate. Whereas if it's a very steep curve, it might be something like rate equals K, A to the power 2, because doubling the concentration of A would mean that the time is a quarter of what it was, or the tangent, the gradient of the tangent would multiply by 4. It would be 4 times as fast. Those are sometimes quite hard to see, so what we sometimes do is turn time into rate by doing 1 divided by time and plotting that up the y-axis against the concentration of reactant A. If you get a straight line in this case, rate against initial concentration of reactant A, it means that the rate isn't changing despite you changing the concentration of A. If it's a straight line going up, then that means its order with respect to A is 1, because doubling the concentration of A doubles the rate. And if it's a curve, so doubling the concentration of A actually makes the rate maybe increase by 4, then the order with respect to A is a 2, because doubling A to the power 2 then would make the rate 4 times bigger. There is another one. They've never asked really a question on it at all, but you can do log of rate against log of concentration, and the slope of the line is equal to the order of the reaction. But that's very rare, and they've not asked that in a long time. Let's just have a look quickly at specimen set 2. Question number 1.2, they did something tricky here. It's a straight line, but actually if you look along the bottom, it's not concentration, initial concentration like in the bottom 3 graphs. They've squared it. It's concentration squared. And just a point of note, I'm not going to do the maths on this one, but if it's squared along the bottom, instead of concentration, if it's squared, concentration squared, a straight line is second order. It basically turns a curve into a straight line. And then finally, the last part of this question, a role of something. So a role can be an oxidizing agent or a reducing agent, but in this case it's a catalyst. So the role of the Cn minus is a catalyst, because actually if you look at the reaction equation, Cn minus, which is the, they're asking you the role of that, doesn't appear in the reaction equation. It's not taking part in the reaction, but it does appear in the rate equation. There it is, concentration of Cn minus, so it's affecting the rate but not reacting. Or if it's reacting, it's remade overall and therefore acting as a catalyst.